Here is a non-inverting amplifier circuit built with the LM741 op-amp. The input signal goes to pin 3, the non-inverting terminal. Resistors R1 and R2 connected to pin 2 set the gain. The formula is Vout equals VIN times 1 plus R2 over R1. We want a gain of 10, so R2 must be 9 times R1. We selected 1 kilo for R1 and 9 kilo for R2. With these values, any input voltage will be amplified by 10 times at the output. Here is a simulation running. As we increase the input from 0 to 1 volt, the output increases from 0 to 10 volts. The straight line on the graph confirms linear amplification with no signal inversion. Now here is the same circuit built on the breadboard. The LM741 is powered by plus 15 volts on pin 7 and minus 15 volts on pin 4. We apply a small DC input voltage and measure the output with a multimeter. At 0.2 volts and we measure 2.59 volts out. At 0.4 volts and we get 3.84 volts out. At 0.6 volts and we get 6.10 volts out. At 0.8 volts and we get 8.24 volts out. At 1.0 volts and we get 10.36 volts out. The gain calculates to around 10.1, which closely matches our target. The small difference is due to resistor tolerances since our actual measured resistors were not exactly 1 and 9 kilo. Now here is the inverting amplifier circuit. The input goes through resistor in to pin 2, the inverting terminal. Pin 3 is connected to ground. The feedback resistor RF connect between pin 6 and pin 2. The gain formula is Vout equals negative RF over RIN times VIN. We want a gain of negative 10, so RF must be 10 times RIN. We selected 1 kilo for RIN and 10 kilo for RF. The negative sign means the output will have opposite polarity to the input. In the simulation, you can see when the input is positive 1 volt, the output is negative 10 volts. The output is 10 times larger but inverted. Plotting the points gives a straight line with a negative slope. Here is the hardware version on the breadboard. We measure the output at different inputs. At 0.2 volts and we get negative 2.19 volts out. At 0.4 volts and we get negative 4.49 volts out. At 0.6 volts and we get negative 6.88 volts out. At 0.8 volts and we get negative 8.86 volts out. At 1.0 volts and we get negative 10.51 volts out. The gain averages around negative 11, which is slightly higher than negative 10 because our feedback resistor measured 9.71 kilo instead of exactly 10 kilo. Both circuits successfully demonstrate how operational amplifiers can be configured to perform precise amplification for real-world applications.